Good afternoon, ladies and gentlemen. It's my pleasure to welcome you all to the 2024 ECTI Distinguished Lecture Series. It's lecture number 3. I would like to begin by acknowledging the organization that have made this event possible. This distinguished lecture is technically sponsored by the ECTI Association and IEEE Thailand section, with Chulalongkorn University generously hosting us today. We extend our sincere gratitude to these institutions for their support in fostering academic excellence and knowledge sharing. Today, we had the privilege to hearing from a renowned expert in the field of electrical engineering and computer science. Our distinguished speaker is the Professor C.C.J. Guo from the University of Southern California. Professor Guo holds the position of William Hoff Professor and is a distinguished professor of electrical and computer engineering and computer science. He also served as the director of the Media Communications Laboratory at USC, which is University of Southern California. Professor Guo will be presenting on the topic recent developments and outlook in green AI ML. These lectures promise to shed light on the evolving landscape of the artificial intelligence and machine learning, with a particular focus on sustainable and interpretable approach. As we dive into the world of green AI ML, we will explore the journey of AI since its inception in 1956. Examine recent rapid advancements and discuss the societal implications of these technologies. Professor Guo will also introduce us to the concept of green learning as an alternative to the current deep learning methodologies. Before we proceed with our distinguished lecture, we have a special presentation to make. It's our tradition to express our gratitude to our extreme speakers in advance of their talks. At this time, I would like to invite Professor David Manjerpongchai, the president of the ECTI Association, to come forward and present a token of appreciation to our distinguished speaker, Professor C.C.J. Guo.
And I would also invite Professor Supawadi, the president of ECTI Thailand section, to give the token of appreciation to the MC today, to MC.
Okay, let's start our distinguished lecture. Professor Guo, the floor is now yours.
Yeah, thanks for the kind introduction and also the, the hospitality. So it's my pleasure to give a talk about the AI machine learning, and particularly the green AI and machine learning. It seems not working. It's not working. It's still. Okay, go back to the. Okay, yeah, the AI. This term was coined at the workshop held in Dartmouth in 1956. But so I would like to explain a little bit about the definition Okay, next. So actually there is an earlier test called Turing test in 1950. So Turing test basically says you're a person C, and then there's a curtain, and then you're between a computer A and also another person B. And the interface between the A and C or B and C just through the dialogue. And if you cannot differentiate A and B, which is a machine, which is a person, then that basically the machine passed the Turing test. And that's the definition of AI. Okay, that's according to the Turing test. Okay, next. But actually, some people like John Serra challenging this definition. So he used an example. So there's a closed room, and then there's a person inside, and this person communicates with outside through the slip, like some kind of written notes under the door. Okay, so the person will ask some question in Chinese, and the person inside the room, he did not know any Chinese, but he has a lot of powerful machine with him, so he can using those powerful translation machine translate Chinese to some language he's familiar, say English. And then he can find all the answers and then get the answer and then translate back to Chinese and put the notes under the door to the outside world. According to the Turing test, this person knows Chinese because he can communicate with the outside world with Chinese easily. But the person actually in our human definition, he does not know any Chinese. He still just use a lot of tools to help that. Next. So here, okay, go back to previous one. Yeah. So here we have two definitions. One is a weak AI, one is strong AI. So weak AI is like according to the Turing test. So you try to simulate a person's mind, but the person or the machine may not understand any semantics. And the machine does not have any logical reasoning capability. So actually ChatGPT is something like, ChatGPT in most cases can pass the Turing test. So people feel now you talk to ChatGPT just like a talk person. So you're very happy about that. Of course, ChatGPT also made some mistake. But the strong AI basically, it's a real person, so he has a mind, okay, and he understands the semantics and can explain the logical flow. So I want to use more example to explain the difference between weak AI and strong AI. So next slide. So for example, you want to recognize dog and cats, and children can recognize dog, cats with very few examples. They may see only maybe 10 dog, cats, then they know the difference. But in the early training data set called Kaggle training data set, there's a 2,500 dogs, 2,500 cats. And if you ask a person to watch so many dog image and cat image, you forget it, a lot, right? So, but humans don't do this. Humans don't use that. And another example is there is a scientist and the chauffeur, the driver for the scientist. And the scientist gave us talks many times. And his chauffeur listen the talk many times. So one day scientist said, let's do an experiment. You go to the stage and give the presentation for me. Okay? The chauffeur just explain everything nicely. And the audience surprised, right? And the audience asked him question, the chauffeur question. And chauffeur say, this problem too easy. I asked my chauffeur to answer the question for you. The chauffeur sit there is the real scientist. So it means just, who is really knows, who does not know, but pretend to know. That's interesting. Another is like take the math exam. So I have a high school classmate. There's something a little bit difficult, and he asked me how to, and I explained him the rule and the reasoning. And he said, "Oh, your explanation too difficult. I really couldn't. But I remember the answer of this kind of problem, so I can do it." But my friend, he did not know anything about that problem. I know that. Okay, and another is basically some people say when you take the exams, you don't want to take the A or D, A, B, C, D. You choose the middle B and C, right? Because the chance of the B and C to be the correct answer is higher than the A and D. Okay, so that's the, okay, yeah. So you can see, I hope you can see the difference between the weak AI and strong AI. Okay. Now let's come to the AI. The AI, there is very little progress from the definition of AI 1956 to 2012. So in the beginning, around 56 years, it's very slow. But then up to 2012, there's a rapid development. So now this become the AI era, right? But what make the difference? So will you think people are less smart in those 1956 to 2012, and people become smarter after 2012 and can develop AI tool? I think you probably will not accept this kind of explanation. So there are two things. One is after 2012, there is a very large data set released called the ImageNet, and it has 1,000 object classes and have the 1.4 million images. On the average, each object class around 500 images. And then there's also the neural net solution. So in the first round of the competition, neural net solution outperform other pattern recognition solution by a big margin. And that's also another way. People suddenly feel neural net actually died many times, okay? Went up and died, went up, died several times. But now this time, they came out strong, okay? The neural net research now came out very strong. And the network they use called AlexNet. Okay. So these two, they make everything change. And now we have even ChatGPT and so on. But I want to give a little more explanation about this. So the real reason people fail in the old day AI was because people had some methodology belief. They think the AI has to mimic a human being. So human can learn from small data. The computer has also learned from small data, okay? And they hope this developed solution can be well generalized like a human. So this is called a weakly supervised learning. So with very little supervision, and your learning algorithm better independent of data. But this is a very challenging goal, okay? Actually, it's just hard to get a good result along this path. So for example, we talk about image understanding. The classical approach is you have to do edge detection. Then you do the segmentation, and then gradually find. But this path, computer vision used for 50 years, moved very little. Computer vision just did not move much, right? Now you give up this approach, methodology. And I think that's by accident, because the ImageNet and the neural net, by accident. So there is after 2012, people start targeting weaker AI. So I don't want to mimic a human to be able to come up with something generalized well. I want something just give a very large data set. So you have a lot of dogs and cats. And I don't need to understand the anatomy of the cats and dogs. So cat dog has a head, 4 feet, body, tail, don't care. Okay, I just give you a lot of cat dog images. And then you find a AI model that split dog and cat classes. Okay, and then you hope this can differentiate in the testing cases. So actually, I joke with my student. These days, the AI is the computer vision. For example, computer vision, they don't know the age. So the computer vision without age, right? And the language learning, language without grammar. But then you ask, we can say, well, all the grammar, linguistic, all bad. But if you ask human learn English, do you need grammar? I think we need grammar in order to generalize. If we don't have a grammar in the high school, in the elementary school, we cannot learn the English so effectively. So we need grammar. But now the machine is there. Don't worry about grammar. Just watch millions of the articles, Wikipedia, inside, all the things. You just watch so many things. You learn grammar by yourself. But human cannot learn this way. So now this is really a very interesting time. Okay, do we really honor this kind of just large number of data, and the human just cannot do it. Okay, so this is a very different thing. And another very interesting example is when you try to do the object recognition. So there are object with airplane. An airplane image most come with the sky background. Okay. Now I give the computer an image without object, just only sky. If the computer is smart enough, the computer should say no object, right? But no, the computer will say airplane. Because the strong correlation between the sky image and the airplane image with sky background, and the computer does not segment the object. So actually, this is just a very different methodology. So it's progress so fast, not because the humans are smarter, but just people change their methodology. Now heavily rely on a lot of training data. Okay, so I don't want to say, today the AI just much better than all day AI. And today actually a lot of problems. So let's give more examples. Visual salience. If you have very few training example, visual salience is a very difficult problem. Like a cat is visual salient, horse visual salient, 3 people visual salient. And people just couldn't find a good feature for the visual salience. Okay, but if you change the problem, I give you a million of images with the object and salience, object and salient. You see so many pairs and horse and so on. Then I give you another object, say, where is the salient? And the computer can do it. Basically, they use some regression approach. They learn from a lot of examples. And you better your testing image has some correlation with the training image. If testing has nothing to do with training, then testing performance usually not good. But if you have strong correlation, then the computer can pick up those salients. So I told my student, actually, you change the problem from very hard problem, which is like a strong AI, to a much simpler problem, which is weak AI. You know what I mean? You just use heavy supervision to change the methodology. Another example is a depth estimation. Again, if you have very few training sample and say, what the depth? But human can do depth estimation very easy, right? We don't see a lot of example, don't see a lot of pair, and then to do that. Human can somehow find some cues to know the depth. But ask a computer to do that, very difficult. But now it's become very easy again, because just a lot of training data. Give you the pair image, depth pair image, that give you hundreds of thousands this kind of pairs, then the computer can do it. Quite a good job. Okay, so I will say the driving factor in modern AI actually are 2 things. One is we suddenly realize actually we shouldn't take the strong AI approach. We should take a weak AI approach. Use a lot of supervision to help the AI. Okay. But second, you also need to find a mechanism that can benefit this large amount of data. If you cannot utilize this large amount of data, then you will not be able to get good result. And traditional pattern recognition, they cannot leverage or benefit from this large amount supervision. Okay, so what is supervision? So supervision basically is a paired input-output. Okay. So depending on different application, sometimes it's just a dog, cat, this kind of label. But sometimes it's called the self-supervised learning. So self-supervised learning, basically you can have some kind of super resolution. So this is about the pair. So one supervision is input is the image, and F is a function, is a mapping, and output is a label, pair. This semantic label, usually you need a human. You cannot ask computer to do it automatically. But of course, today, once you train the AI, the model can help you to find the label. And then there's another case, it's a segmentation, and then there's based on the class, say bus class. So in the top, it's just bus. I don't care about 1 bus, 2 buses. So that's a bus. The second lower one, I want to do instant base. So it's not only car, but 2 car. So you want to map. So basically it's an image, but you map to a pixel domain, and each pixel you give a label. And this is another thing, is 4 dogs. Okay, so you need count. There are 4 dogs. And you provide a lot of this kind of pair. This is another example, is given the left-hand side images and right-hand side, you can either say the object is a car very small, a person, a motorbike, right? And also you can ask people to write sentence descriptions. And then you can use this to train. You have a lot of this kind of image and sentence pair. Then you give an image, you can ask the machine to write down the description. So the caption, automation, the caption recognition, caption extraction. Okay, another is now today we use the ChatGPT. It's you have the mask the word. So the lower one is the desired output. You can get that many sentences, and you can mask, right? Is intelligence or intelligence exhibit or something about the computer system. You mask them and you get the output. So these form a pair, and this becomes a very fundamental unit. That's to transformer block, and you have multiple transform block. You can train the more advanced like ChatGPT natural language processing system. And this is super resolution. Again, the input will be low resolution, output will be high resolution. But the way people generate is people start high resolution and shrink to the low resolution. And then there's inverse mapping. Okay, you have many of this, and then we apply to the low resolution, and we want to see the high resolution. So the key is about the pairing input output. So, but the design and the preparation of training data is costly. Okay, that's but now a lot of students, they are not able to solve problems. When they did a C problem, they just say, Professor, give me more data, give more label data. I have more label data, I can solve anything in the world. Okay, but you don't give me any training data, label data, I cannot do anything. So that's very funny. Okay. So we want to from data to the computational model. And so now we talk about how deep learning exploit that. So first you have to collect suitable training data for a given task, right? But the one question is the more the better. Actually, the answer is yes or no. Okay, it's both. I think the more the data, usually you cover more diversity. So that's good. But actually, the more data you have, actually, there are easy data, there are hard data. And easy database is a high percentage. So there's a big portion of the data that's called easy data. Hard data is very few data. So it's like 1%. Okay. So 1% means you get 100 sample, you get 1 hard data. You get 1,000 sample, you get 10 hard data. Those hard data actually is the most valuable, but you have to get in a difficult manner. If you don't do it smartly, you will just need a lot of data to get that small percent. And that's one. So the more the better may not be necessary. Okay, I think the more is basically I want them unusual data. That's more important. Like an MRI image doctor. If you just let students see all the data, actually most of are easy data. But some professor has experience, very old, very experienced professor. He has a couple MRI images are very difficult to know. And there are some clues. So if they show students all this kind of secret recipe in his pocket, they show, oh, these are the MRI images, hard to learn. And student will benefit the most from that. You know what I mean? The easy, just you don't need a lot of easy data. A couple of easy data, students just get it very well. And also, of course, your training and testing has to be correlated. Otherwise, the training will not help your test much. Okay, so that's about data. And then the next one is about the neural network. So neural network is a parametric model. So it's really a parametric model. It's somehow the first design is a non-trivial. Okay. But very few people can really come with a totally new network. So mostly is you copy someone backbone and you add some peripherals. Okay. So this backbone, there are several very famous examples. Okay. And then once you get that, I will say 99% people just use the standard one. And not only use standard one, use the pre-trained one. And this all AlexNet, VGG, they all pre-trained by ImageNet. Because that's the only thing available in the public domain. So if you tell the patient, I use the ResNet to analyze your cancer cell, right? But this ResNet is pre-trained by ImageNet, means dog and cat. So how doctor explain the patient? I use a dog and cats pre-trained the retina to find you have cancer and with lesion. So the patient will not buy it. Why my lesion, it's like some cancer cell, has something to do with dog and cat. So doctor sometimes has a difficult time to explain that. Okay, and then once you have the model, and then the parameter is very straightforward, just backward propagation, and that's your one line, like Python or PyTorch. Just one line do the backward propagation. You don't need much. You don't need to know much. Okay, so so there is a example like called Lacan network, 5-layer. So he proposed that in 1998. The paper was not paid much attention at that time because that's at the wave of the neural net. And neural net already went down. So that paper wasn't. But of course, today is highly cited. By that time, people don't care that much. So there is all the neuron basically has this operation. It's a convolution operation. So if you look at the neuron, basically there is a convolution operation and plus a bias term, and then you have nonlinear activation. Okay, and the most mysterious part for the people basically is nonlinear activation, right? That's make the system like nonlinear. And many people told me, neural net is so powerful because it's nonlinear. Okay, but then my question is, how this nonlinear activation helps you? And almost no one can answer me. Okay? So when I started this about 10 years ago, my first question to my PhD student is why we need nonlinear activation. What's the role of nonlinear activation? Okay, so that's the question I have for my student. And actually there is another system require the backward propagation. Okay? The backward propagation like a deconvolution. You have the output Z, right? You want to know the input X. Also, you need to determine the coefficient parameter A. So it's a deconvolution problem. And there is a famous Viterbi algorithm. There is a forward convolution, and you want to do deconvolution. And in Viterbi algorithm, the X is interpreted as a probability. So X is non-negative. So you can carry out the deconvolution in a straightforward way. But now, if you don't have nonlinear activation, your X can be positive, can be negative. And that makes the deconvolution very difficult because the A and X, they can be both positive, they can be both negative. If they multiply together, they all contribute to positive, right? Another is A is positive, X is negative. They have opposite sign. You multiply together, you get negative. So these are the 4 cases, but it become grouped two part. So making the summation, it's very hard to find the right X and A. Okay, but if you do the make a nonlinear activation from the previous stage, so basically in the previous neuron you have nonlinear activation, you make X to be non-negative. Big non-negative, then A can be positive, negative, but X it has to be non-negative. Just like a Viterbi algorithm, you ask X to be probability, so probability is non-negative. So that's basically I call this sign confusion. So when the 2 convolution filter in cascade, the convolution is basically cannot differentiate the following 2 cases, 1A and 1B, okay, because both positive, both negative. And then the case 2A and 2B is 1 positive, 1 negative. But if you do nonlinear activation from previous neuron, then you basically remove the B, so only have A. So then you can carry out the convolution smoothly. Okay, so that is the paper I wrote in 2016. Actually, I wrote in 2015, and no other student want to do, so I have to do it myself. Okay, so I think that's a challenging the professor whether you can survive without a PhD. Okay, so this shows the difference. If you have the only linear, no nonlinear activation is the red. But if you have a nonlinear activation, you cannot green. So it means x is epoch, okay, and y is the loss function. You want loss function as low as possible. So if you add a nonlinear activation, you are able to push the curve lower, and then the saturation, then usually the saturation will call the vanishing gradient. So the gradient becomes 0. So that comes from the confusion. So you are able to push the vanishing gradient to a later stage, later epoch, and the loss function lower. And that the left-hand side is MNIST, right-hand side is the fashion MNIST. And the accuracy with nonlinear deviation improved by 2% to 3%. But for the ImageNet, you can improve by 8%. Okay, so two different data sets, you have different improvement. Okay, now then we have AlexNet. If that's a generalization of the Net5. And this is one, the ImageNet test. And this is VGG16. And you have the 16 layers. But this fundamentally all similar to the Net5. So this kind of architecture is one problem. It's if you have a certain module, you get a vanishing gradient, means there's no gradient, become gradient 0, then the whole system cannot learn. The whole system stops learning. So even there are some modules still have a nice gradient, you can still go down, but one particular slice, one particular layer, 0, no gradient, then it stops. So the people, actually He Kaiming wrote this ResNet, and he introduced the skip. So this skip, when he tried, I read his paper, tried to understand what he want to explain this architecture. I really couldn't follow his argument. It's very difficult to understand what he want to say. But now we look at this idea. If you worry the most is a vanishing gradient, so gradient becomes 0, then you can use a skip. So this part is 0, I just isolate this part. So this part will not appear. Then I will skip and then bypass that. So this bypass is very powerful because you can delay the vanishing gradient to happen. So you have a lot of modules all get a vanishing gradient. Then the whole system get a vanishing gradient. Otherwise, you just bypass. You have another path. Okay. So I think that's another way to explain this vanishing gradient. And then there's another one, DenseNet. It's a lot of skip, right? So again, it's just a delay the vanishing gradient. So the curve, learning curve, the loss function can go down lower and lower. Okay, so these are about neural net, but there are concerns. So mathematically, you cannot explain. And you can attack, it means change the input image slightly. Humans still see dog, cat, but your decision, the network decision can be totally changed. And then you need a lot of supervised data, label data, and you consume a lot of electricity, generate a lot of carbon dioxide, so-called high carbon footprint. And also, I mean, for the doctor, they may not know your mathematics, but doctor need to know the logic. Actually, I work with a lot of doctors. Doctor working very hard, and doctor very smart. Doctor may not be, mathematically well trained, right? But doctor can follow the logic very well. You cannot fool a doctor using very strange logic, okay? But doctor look at deep learning, they just puzzled. They say, what's going on here? And ask all the scientists and engineers. No one can give doctor a good explanation. Oh, black box, it's too difficult to explain. Just trust the result. Always work. We'll take you, will you take that? Doctor cannot take that, okay? Okay, so the current deep learning practice is one, data collection and labeling, but you have poor understanding of the data. You really don't know what data play what role. And fine-tune the neural network, in particular, use a pre-trained model. You don't touch that. And also usually pre-trained by ImageNet. And these days now you have the large language model pre-trained by what? We don't know, right? It's a pre-trained like a Meta Llama 3. And what Meta trained that Llama 3 model, you don't know. But no one can, particular academic people, can touch that. You cannot touch that. You just accept it as is and add something peripheral. So that's our contribution, the academia or whatever. Just very little contribution, but big black box in the middle. So we have poor understanding of the model. So I told my students, basically, you're just struggling with data cleaning, and then the network architecture, and you just borrow a big architecture, and then you don't have the computer to run, you don't have the server to run, and then the hyperparameter fine-tuning, and basically you are buried in implement detail, just codes, right? So it's kind of a very sad story, but that's the most active research now, right? I say it's engineering. It's engineering, but it's not really science. Okay, so look at just one example, ChatGPT 3. There are 175 billion parameters. You train this model in 2020, it costs is $4.6 million for that. And ChatGPT 4 now it's a claim of human brain. Okay, but it's 100 trillion parameters. Okay, and the cost is like you need $325 million to train. So this is just unsustainable. And the NVIDIA want to keep selling you a more advanced GPU. The GPU after 2 or 3 years not good enough. Change it. Like an Apple iPhone. They keep asking you to change the iPhone. And now they keep asking you to change the GPU car. A professor just cannot do that. There's no way we can survive with this competition. Okay, so now the thing is, I need to respect supervised learning, okay, heavily supervised. I think I'm not going to challenge that because heavily supervised learning is make today AI successful. If you went back to the weakly supervised like human, I think progress will be very slow. Okay, so I need to give up. I have to give up that, but just say, well, it's heavily supervised learning, but can I do another approach, not deep learning, but something else? And I've been struggling with this for 10 years. Okay, that's I never had such a tough time in my life. Okay, but also I will say I never have such an enjoyable time because you explore in the dark. Okay, so I started with something, and then I met a very good friend in Samsung, at that time CTO, and he asked me, say, well, what's your new method? I say called successive subspace learning. He said, bad name. And then say, I have a name in mind, but I feel it's too arrogant to call it. So what's the name? I say green learning. I say good name. Okay, keep that good name. And later on, I honor that. I think he suggests a good name is a green learning. So green, what the green learning means? Basically, it's a low power consumption, small model size, the number of parameters is small, and allow logical reasoning. So that's really the thing. And the difference between the green learning and deep learning, there's no neurons, there's no network. It's based on non-parametric modeling. It's non-parametric versus the so it's just like signal image processing stage by stage. It's modular design. It's not a whole end-to-end, and it's feed-forward training, no backward propagation. So in some sense, green learning is totally different from deep learning, but still use this large supervised approach. Okay, but green learning can scale well with small amount of training data. If the training data is small, green learning still works. It usually works better than deep learning. Okay, so I will just quickly talk about green learning. So there are 3 modules, and we go feed-forward. In inference, it's feed-forward. In training, also feed-forward. And training, actually, the complexity is even much lower than the deep learning. So first, they try to find some representation. And it's to try to look at the correlation between some, say, pixels, okay, or the word or whatever. So you find the representation. You don't need a label to do that. And find rich representation. And then among the representations, then we will choose good representation can be the feature candidate. So then how to choose that? We have to use a label to help us. And then we also can try to generate new features by considering a linear combination of the raw features. Okay, and then final stage is like a machine learning tool like XGBoost and so on. So the real thing about this actually is the middle. Okay, and the beginning we spend a lot of time. We try to find supervised representation learning. We introduce a called the sub-transform. But sub-transform basically it's you have the say 5x5 patch, and you take the DC local mean, remove the mean, so that the residual signal is a zero mean signal. And then the zero mean signal, you can do the PCA. Okay, so we can do the AC component. So there's a DC component, you take local mean out, and then the rest is zero mean, and then we can do PCA. Okay, and if you do feed-forward, there's no sign confusion. Sign confusion comes from back propagation. In our system, we don't have backpropagation, so no second combination. And it's unsupervised learning. You just look at the pixel correlation. So different pixel, like texture, a certain pixel correlation, and image number has some pixel correlation. So we try to look at that. And you can do Fourier transform, you can do the wavelet transform, you can do whatever transform you want. Okay, so that's very flexible. But now the thing is, you have a lot of coefficient, say sub coefficient, or PCA coefficient, or wavelet coefficient, or DCT coefficient, Fourier coefficient, all these kind of coefficient. Each coefficient is a single dimension. And I can use that as a candidate for the feature. So here I compare two features, feature A and feature B. Feature A is good feature. So there is a one-dimensional. So there's a minimum, there's a maximum, and there are two, say, binary decision. And feature A, there is some cutting point. You can separate the orange and blue well. Feature B, you cannot find the good proper location. So feature A is better than feature B. Okay, so that's a high level. So now the thing is we have to learn is finding the cutting location. So we search those cutting locations and find the best location which minimize the entropy. Entropy means not mixed, right? So entropy lower means more separable. So we can using that. So the way we do is we have the F is a one feature, and then the minimum there's a maximum range, and then the blue dot based samples. Okay, so we have a lot of samples, and they project to the feature. There's a projection, vertical projection about the feature value, and then we have the boundary split the feature into left half plane and right half plane, and this boundary can move, and then we can calculate the entropy. So the classification task, I think there is a discriminant feature test. So basically left-hand side the entropy, right-hand side entropy. Then we consider weighted entropy. The lower one is a regression. So left-hand side we have the mean, right-hand side of the mean. And then we find the mean square error for the left and right, okay? So then we consider weighted. And then we will consider the different bin. So the capital B bin and B equal 1, 2, 3, and so on. So that's the search point. And then we find the point which minimize the loss function. So that shows the feature that at the best location splitting, and we are able to get a lower value, lower loss function. So using this, and also I show the different partition. So you can partition 16 or partition 64. And actually, the curve is very smooth. So your partition 16 bins will be about the same of the partition 64 bins, because the lowest point is very similar. That reason is a lot of things will not change. When you move from one location to its adjacent location, only the middle part change. The other part still the same, left, left, right, right. So you can move without, so the whole curve basically just smooth. So you don't need many bins. So typically we use 16 bins. And then we can order this loss function coding the feature index from the smallest to the largest. And then we can pick the beginning one as the feature of the good feature, okay? Because the loss function is lower. So that's about feature selection. But there is an issue is we use the discriminant feature test to order the representation. But this representation is unsupervised. You don't have the supervision label. So even you get the best feature from this candidate, they may not be very powerful, right? So we also think about another way is, can we combine these raw features and to generate more powerful features? Okay, so the number one question is, there are many features, thousands or even millions of features. And what feature you want to do combination? So you need a systematic way to do that. And then what the weight to do that? So we have some idea to do that. So we use the XGBoost to run the feature. And then there's a tree, the boosting tree. And then there's a conditional probability. So at the root node, there's a feature you select, split the left and right. And then under that, there's another feature you select to split. So this conditional probability XGBoost provided actually explain this feature are in certain way, they are good combination. So if you want to consider joint probability, you better use the feature along the path. So you have XGBoost, you have different paths, you can combine those features together. So that's give you a subset of feature to do the linear combination. And then the coefficient of linear combination, you can basically use the least square. This called the least square normal transform. So it means in a low dimension space, say three dimensions, the three features. And how you combine them? You basically find the gradient in that subspace and then project your feature to that gradient. So that gradient becomes the coefficient, projection coefficient. So that can be done very efficiently. So I show the examples. So you see the feature. The green one is original feature. The yellow one is the new feature. And the Y is the the loss function. The lower, the better. So you can see using this kind of least square normal transform, we can generate much more powerful feature than the raw feature. And this feature actually, it's a very competitive with the deep learning feature. So basically, without those very backward propagation, blah, 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 we just do this feed-forward statistic-based approach. We can get those strong features. And the sub filter we design, we only need to say a sample like 10% of the sample to learn the filter. Okay, we can show that, the proof. So we use statistics to choose the filter, and we also use statistics to choose this. So it means when I show those blue dot sample, we also use 10% of the sample. We can find the feature very robustly. So we heavily use statistics to simplify the computation in the first module, the second module, and so on. So in our framework, statistics, linear algebra, and the probability, everything just very powerful can be used. I mean, a lot of double E students learn a lot of math in their life, but then come down to deep learning, just everything useless, right? But now we reuse everything, and so students get very excited because they think the math actually is still the most powerful thing, right? Okay, so now we compare three things: pattern recognition, deep learning, and green learning. So there are three modules. The pattern recognition in the past is you don't have anything. You need a human insight to provide a feature, and then feed the feature to the machine learning like SVM or the XGBoost or whatever, right? So the blue one just all need a human, but the deep learning is everything just supervision. Use the backward propagation, propagate the error, prediction error, and adjust your parameter so that you can, next time you do a better prediction, narrow the gap, right? The loss function narrow, making the loss function lower and lower. It's a very slow process, okay? And the last one is our approach. The first one, representation, is just no supervision. We can just using statistics find the filter. You can also use a fixed one, not adaptive one. You can use the adaptive one. But no matter what, you just go to the feature learning. So you can, using label, heavily supervised label to tell you which feature is better. And then you can use the feature combination to generate new feature, but more powerful. And finally, we use the traditional machine learning like XGBoost. Okay, so it's modularized, so you can explain. If end-to-end, you really cannot explain. Okay, so we have some example. This is a fake video and how you differentiate fake video, and from the ground truth video. This problem, very important to our society, but actually it's not a very difficult problem. So there's a first generation data set, and the training sample is very small, and so that makes the performance very bad. The above the red box is most of the deep learning, everything deep learning. And the red box is our solution, green learning solution. And our accuracy actually better than deep learning solution. So for the UADFB, we get 100% accurate, right? FF++, we get a 99, 98. You look at the model side, how many parameters you have? We have less than 1 million, right? But the other all like 22 million. And the 20 million is basically uses ResNet. They all use ResNet as the backbone. And the second generation, again, our performance is very good. Our model size is very small, and you can see all the best performance actually is green learning. Another is about the quality assessment. So a lot of visual quality is user generate, like a YouTube video or video conferencing. So you don't have the ground truth, you just have to compress the video. So we need to do this called blind quality assessment. So you need training data, build training data to do that. Okay, and so we also have very good result. There are 4 columns or 4 rows. The first one, the second one is using the pattern recognition approach. The third one is entry-level neural net. And the fourth one is advanced neural net, means use a pre-trained model. And our performance, the last one is the red box, is green. This is for image quality assessment. We are in this group, very similar to the advanced deep learning. And our model size is like 1. The other model size is 30, 40, right? And the flop we have is our flop normalized to 1. The flop they have, this is inference, not about training. The inference is like 600, 800. So we can get 800 image evaluate. They only get 1 image evaluate, give a score. So you can see the speed difference. And some people ask me, why not you compare the training time? The training time I cannot compare because they didn't give me the training time information. They didn't report anywhere. They just give you the model. So you can run the test, but I cannot. Training, I believe, the order should be 10 to the power 5 or 10 to the power 6. The training difference even much higher, okay? But this is about testing. And this is another one is a video, okay? Green video, blind video quality assessment. So you look at our performance, the best one is the lead, right? The bold face. And our solution, either number 1, this or number 2 under bar. So if you look at the model size, it's much smaller, it's less than 10%, more smaller than 10%. And then you look at the flops, again, that's huge difference. 2 order of magnitude, close to 3 order of magnitude. Okay, and I want to also comment about lightweight deep learning and green learning. Lightweight, basically, the first you have to train the full network, high performance, and later start to prune the network. And usually you can push the network maybe 10% of the original size, but performance with some small degradation. But green learning, totally different methodology. You just design a system from scratch, okay? And the model size usually much smaller, like 1% or 2%, okay? And the prune cannot go to that degree. It's just no way. So basically, you have to change the methodology. Okay, so the conclusion and outlook. So I think when we look at the AI, we need to look at the whole thing, right? Technology, regulation, ethics, and so on. Okay. So when you evaluate AI machine learning, I think we should pay attention to the 3 components, right? Effectiveness. Effectiveness means the performance, right? Accuracy, quality of generation, and performance scalability, this kind of thing. Efficiency means how large what storage you need, right? Store the model, what computation you need, how many carbon dioxide you generate, this kind of thing. But I would say most AI people totally ignore efficiency. And people talk about efficiency usually is environmentalist. Okay, those are people, environmentalists say, oh, there's too much carbon dioxide. But those AI people, neural net people, they just say, well, who cares? Okay, they just keep building larger server. So how expensive that kind of server, right? But they don't really care, environmentalists. These 2 will collide, right? These 2 trends will collide. But you think which will win? We all predict the AI will win. Environmentalists, people say it's very important, but we always hold that. We won't die tomorrow, right? But AI, we don't get the AI game, we lose money tomorrow. So that's a very bad thing. But unfortunately, human, I have to say, short-sighted. Most people just short-sighted. Okay, and the NVIDIA, they just want to make a lot of money, just selling a lot of chips. Okay, another thing to academia people, in my opinion, is interpretability is the most important thing. If we cannot interpret the system, what's our value? You know, our value is not making money like NVIDIA CEO or something, right? So if you cannot interpret how you diagnose it, how you predict the error case, and how you know how far you are from the ideal, what's the error and so on, you need to be able to predict the capability of the system. Now the total system is a black box. You cannot interpret. And if students accept this, then students become hopeless because their PhD training for what? Just good engineer, but don't know anything. Okay, so anyway, it's kind of sad, okay? And so key question you have to ask, like, what kind of supervision we introduce, like ChatGPT and so on, right? Attention, you know, that's a very important part, okay? Because of some of the image is very large, and you need to know attention. That's very important. But most attention people talk about is back propagation based attention. Yeah, after you train the system, and then we say, this image, what the attention is. They use the prediction and coming back. But we need to develop a feed-forward attention mechanism. And this is like my dream for a while, several years. I think, how can we get a feed-forward attention? And now I think I have an idea. I know how to do it, but I'm not going to say here because I still work with my students about that. But it's possible, feed-forward attention. So just to look at that thing, that we can find the attention. And then we can use that to design the system. And then the processing, basically, I talk about how to find the best parameter. You use the backward propagation, it's just an empirical lower the loss function, right? And you get a parameter. But you cannot understand the meaning of the parameter. But when you do feed-forward parameter decision, you have to understand every piece of sub-transform, least square normal. You need to know every piece in order to find the forward parameter. So again, it tests your math, right? You really need to be good in math and processing in order to do this parameter design. Okay, so I have an overview paper, and it's about the history, the beginning of the green learning and so on. So if you like my talk, I recommend you to start to read this paper. This paper, it took me a lot of time. The second author is my colleague. Okay, so it's a senior colleague. So he's not a student. Actually, I wrote the paper myself. So one takeaway is first, you have to know the modern AI. What's the make the modern AI different from the traditional AI? It's because change of methodology. You heavily use supervision, and then a lot of things can move fast. Second is neural net is an existing AI solution, but green learning, I believe, is a new emerging way. It's interpretable, reliable. At least you know when mistake occur, you can isolate the mistake or identify the mistake. Sustainable, basically, it's just won't consume a lot of resource. Actually, if you think about the human brain, actually, we may not memorize so much. We may not compute so fast. But in terms of the integration of the different information, human brain is much better than computer. Okay, and we don't need any like water to cool our brain. Our brain is small, but so functional. It can do so many things. But if you go to the AI server room, it's so hot. It needs so much water and to cool the whole system. So there is something wrong. Okay, but of course, you know, if you say something wrong, you go to the CV, or people kill you. You know, people all rejected, right? So that's life. Okay. Anyway, I feel green learning has opportunities, but people always say, "Well, Professor Guo, you finished the ImageNet. We'll trust you. We'll believe you." And then they say, "Professor Guo, once you do a green ChatGPT, we'll believe you." Well, it won't be easy. Okay, it's a big challenge. But I think the ImageNet we should be close. I think 1 year we can get a green solution for the ImageNet. I think it's within reach. And finally, I want to say, in terms of AI, today AI is still weaker than human intelligence in logical reasoning. Okay, you can do very fast computation, seeds, memorize so many things, but in terms of the broad knowledge, right? They can access a lot of data. Okay, but human can integrate the knowledge, and human has a common sense. And those we can build a partner between the human intelligence and AI. I don't think AI will threaten human. I think the thing threaten human is the user of the AI. And unfortunately, a lot of government use AI for the weapon. So that's using AI to kill people. But the bad guy is still the human. The bad guy, we not say bad guy is AI. It's the, who use the AI for whatever purpose. Okay, so that's conclude my talk.
Thank you, Professor Guo, for the very interesting lecture. We have just a couple of minutes for the questions. So anyone, yeah.
Online.
Okay. So anyone who in the online. So if you want to ask question, please ask, or you can raise your hand and I call on you. Thank you.
Or they can type in the chat.
But you can type to the chat as well for the question. Okay.
Thank you.
Sorry.
Thank you. Yeah, it's a great honor to attend your talk. Unfortunately, I didn't have time to join you at lunch, but I'm not an AI person, first of all, and I have been taught to learn that deep learning come to replace all the feature extraction through the human algorithm, something like that, and then it becomes so successful. According to you, I have understood a little better than before that we spend a lot of computations, memories, and we train more with large data set. That's where the success comes in after 2012, right? That's when the data set is so huge, and that's how we utilize machine better than before. Maybe in the past we were trying to follow human too much, but then human learn that going beyond what human can do using the machine can improve a lot, and the success is undeniable. And today I have learned new thing that okay, let's don't spend too much energy, don't do too much computation, and not too much rely on human intuitive. Instead, using some statistical model, somehow you will be able to extract the features. You'll be able to put in classes to be able to go to the next step, which still we will use the machine learning in the same way as before. So we are entering in a new alternative, if I may say that. And one of my colleagues also focus on getting the feature extraction similarly, and not to do deep learning totally. So really, it's a great time to come here and learn from people who work for so long. So we hope that the ECTI distinguished lecturer, which come from your students, I believe these are all your students. Yes, your former students, to organize such an important event in the next in the future. So thank you very much.
Thank you. You have excellent summaries. You get all the points. That's amazing. You get all the points right. Okay. Thank you.
Anyone who online, who joined the meeting online, want to ask question, but you can write down in the chat box.
Yeah. Hello. Can you guys hear me?
Yeah, you can start a question.
Yes. First of all, a very interesting talk. Thank you very much for that. And I just have one simple technical question. So when it comes to feature engineering and feature extraction from raw data, is it always 100% recommended to do feature extraction before model training at all? Or is there any specific types of model that doesn't benefit that much, comparing between using raw data and engineered data when you train the models?
I think the using the again, you want to get good features, but the way how you get that. And now I think in the past, pattern recognition is a human designed feature. But now this is not competitive. Human, no matter what you do, it rarely come out with more than 100 features. Okay? And the deep learning can go to very, very high. They usually after convolution layers, those people call the feature, the deep feature. And then you have the FC layer, that's for the decision part. So they can get a 400, 500 dimension feature easily and even more. The green learning also can do that. Green learning, if you do the representation learning, you can get 10,000 or even a very large number of features. But how you choose the feature, we use the label to help us. Okay, so we start still raw image input or raw data input, and then find some kind of change different representation. So one representation is like spatial spectral, joint spatial spectral representation. Okay, so there is some space, but there are some spectral. Look at larger area. So we have a lot of feature, but then we need to leverage benefit from the large label data. Human design the feature, they only have the majority. Human can only take care of majority, but think people cannot take care of minority. Those are very special case. But if you use this automatic process, do the feature learning, that's green learning try to do. It's without the backward propagation, but just using some feature selection approach and then feature generation approach. But everything is no human involvement, just automatic, and then leverage the large amount of training data. And then we want to get that very powerful feature. Usually also can be 500, 600, or you can even more. But we can get that amount of data easily. I would say easily means very straightforward. And we use a statistical approach and so to lower the complexity. And then we fit the final stage of machine learning. The XGBoost is actually very powerful. And there are a lot of features in XGBoost we can leverage. Yeah, so I think this new methodology, new paradigm, I think right now it's a more, I think it's proven. Actually, we have a lot of applications show green learning can give very good performance. But with a large data set, like a large size, image and so, I think we need to be even more creative. So the one is attention. So one image 224 by 224 RGB color is too large. So if you use the one I described, it will not be very effective. I need to look at the attention, say dog image, but the dog image actually, the dog is just a part, right? The other part not dog, and so I needed to see which part is the dog, right? Which part is a cat, which part is I keep an arbitrary image, I don't know. Maybe airplane, maybe boat, maybe whatever. But I need to go to that attention and then process it accordingly to save the computation. So that's something we need to do for attention. And I think right now, after so many years, so I think I have the idea how to do it right now. So I talked to my student, like yesterday morning, still discuss how to do it. Yeah, once it works, it's just so beautiful because you can understand. So this can be explained. Of course, we need evidence, we need proof, right? But if I say we show that, I can tell you it's so simple. Usually 10 minutes you understand everything. So for the green learning talk, I gave the talk in different places. And I say 1 hour, if you ask people to explain deep learning, 1 hour people say what to say, right? Just give you a lot of architecture. You cannot even follow that talk. But with the green learning, 1 hour, you can learn a lot and you can just logical, right? Gradually you just follow the thinking. So I think green learning should be easier and easier because it's explainable. But if you cannot explain, you just memorize this architecture, that architecture, transformer, one by one. Well, that's very complicated, and you really don't know why, right? You just get the GitHub code and do that. Yeah. So I think that the feature learning is very important, and it has to be automated. If you don't automate that, it's basically back to the old day stuff. But I have to say, many people read our paper cannot appreciate. They always say, everything will know. What's new? So they cannot, and they don't know what's the discriminant feature test. And so they didn't even pay attention to that. They just say, well, this is just a pattern recognition, right? But unfortunately, a lot of people just have no patience these days, and they cannot differentiate some subtle difference. And basically, they think it's just deep learning. You get a bigger deep learning. And that's good work. And something not deep learning, a lot of people just say, well, it's nothing new. So it's a lot of difficult time, but some people need to take the courage to persist in this kind of direction. Yeah. So I don't know whether I answer your questions.
Yes. Thank you very much.
This one question from online. The question is, in the context of discussing super resolution, in your opinion, does generative AI still represent the future of AI to a significant extent?
The super resolution, I think, I have to say, today all the AI actually not about human intelligence. It's just about learn some skill to learn large amount of training data pair. So you're just super resolution, you're the low resolution, high resolution, and give a lot of pair. And then you learn the rule. So I give you low resolution, you can get a high resolution. So basically just to learn that. So I don't think that that's really the good definition of intelligence. But it's a very similar to the Turing test. Turing test basically just I/O, input output, right? So I/O. So yeah. So the super resolution to me is again, it's just about a lot of training and learn the mapping. A neural net learn the mapping. But whether that learning the mapping neural net is very efficient, I put a question mark, which I think probably not very efficient, right? But all day there's a neural net that I see in convolution neural. Now compared to transformer, the convolution neural net is very efficient, right? Transformer even worse, and now everything that become worse and worse, right? But all day now, oh, CNN is very good. But performance not very good. 1% different, 2% different. Performance not very good. Yeah, but it's just we need to do under this paradigm. I think green learning cannot exceed this paradigm. Green learning is still under the paradigm. Heavy supervision and broad learning, the pair, but just change another approach to benefit this new framework, But I don't think the green learning can go to the strong AI. Just I think strong AI is too difficult to reach. And if you want to go that, then everything will become slow again.
Any more question? No, there's no more question online right now. Okay, please.
Professor Ko, because the attendance, they are the graduate student, they are also the faculty in Thailand. I think that it's a good opportunity. I mean, apart from the AI material, I would like to invite you to give the suggestion, some wisdom on the doing research, especially in the limited resource as in Thailand, and also give some wisdom like you all previously taught me during the PhD training to the students. I think that is a very good opportunity because we don't have this kind this opportunity for so often. Please.
Yeah, this is hard to answer. I think for student, the safest way just go with the trend, right? So the major trend, 99.999, all deep learning, but unfortunately, the convolution neural net is over. It's not powerful enough, right? So now it's everything like a bigger and bigger visual transformer. And then the next one will be the large language model and large media model, large foundation. It's so huge. And the university students don't have the resource, right? But now the question is, do you have guts to go another new path? And usually I think this is on the voluntary basis. I will not ask every student, say, well, give up the deep learning, just go with green learning. And most students don't know what to do. They don't have the courage. And a lot of professors don't have the courage either. So, it's a very difficult path. it's 10 years, but for example, I work on the green image coding for 5 years, and we still haven't published any paper. Okay. But to me, I'm okay. The one student already graduated, and he has other paper, but his work is still not very good. But now I have a second PhD working on the coding. But I think now we hold the key. But it took me several years to find the path. So you need patience and you need persistency, and the student need trust you. Now my lab, all the students do green learning. No one wants to do deep learning. They take the deep learning courses. It's okay for them to take, but they don't want to do deep learning. The situation is the same. They just cannot do research for this large model. But they do green learning, they can find some small places and has contribution and so on. But I think most important is that they are happy with the understanding. I think a human, if can understand, no one will choose not understandable solution. But if you not understandable, the only choice, then they just do follow the uninterpretable way, right? So yeah, I think the student need encouragement and they still need the persistency, but there are also reward system, right? They need a graduation, they need to find a good job, and so on. And if they don't see this as possible, then they will go to the deep learning still safer. Right? So I don't know what to say. It's up to the advisor, it's up to the student, and up to the general infrastructure. But I think give some more time. The green learning, I think, will gradually better and better. The position, I mean, now is better than 10 years ago, green learning. So now I went to like Princeton, I went to the different places. They all love green learning because now they sort of also know the shortcoming or the side effect of the deep learning. The deep learning problem become bigger and bigger. So people know this is not sustainable. You cannot do that. So people start to think about alternative. Okay. But whether they have courage to carry out, that's another issue. Right? So I saw a problem.
Actually, the time is almost up, but then again, they have a couple questions coming. So if Professor, yeah, okay, yeah. So because it's pretty rare for Professor Ko to come here, right? So I'm gonna clear the question a little bit more. Yeah, the first question is given that green learning models is more transparent, which is more understandable than typical deep learning. So can green learning tell us when the prediction might fail so that the user can better understand the model limitation?
We can understand either mostly is you don't have enough training sample to cover the particular test, right? So there is a gap between the training and testing. So if there is because we are looking at all about the distributions, right? The testing, there's a distribution of the testing data, the distribution of the training data. If this testing data outside the distribution, then there will be some issues. So I think in most cases like that.
So another one more question. Is it mandatory to have a domain knowledge while doing AI?
I think the domain knowledge is important for application. Okay, so I don't think the green learning, I think the important tool is still linear algebra, probability, statistics, basic sampling, and what else? I think that's about it. That's usually the EE student have the training, undergraduate, graduate, transform theory, this kind of thing. So at the USC, we all have this as a screening exam, right? But if students decide to go to deep learning, they will feel, I don't need a lot of math, right? I think the deep learning model and so on, I think high school student can do it. You don't need anything, right? You just get the GitHub code and then fine-tune the programming. There's no mathematical foundation needed. You say the backward propagation, that's already people wrote the code. Everything people already did. Adam, the optimizer, it's already there. You don't need to know anything. You can do it. So So I feel actually deep learning actually hurting the well-trained student, right? And CS, of course, this day is so hard. The CS students know very little math, like to say. They know the discrete math algorithm about the data structure and so on. But the other math, they don't know. They don't know what's the transform, what's the DSP, what's the linear algebra, or no, they don't know. In fact, they are very happy with deep learning. But I think that the double students should take something which we are good at, right? And then we can develop our own thing. I mean, green learning will be more efficient, that's for sure. But I would say green learning should be also more effective. You know, at least the performance should be comparable. But the thing is, we know the weakness. If we know the problem, we can fix it, like a adversarial attack, right? The deep learning adversarial attack just solve it very ad hoc. But we know, okay, why adversarial attack happened. Then I know how to fix it. So you know the reason. So I think that the EE students should love the green learning because of mathematics. But CS, of course, there's no way. I mean, it's too difficult for them, not linear algebra. So what's that?
Okay. Anyone have more questions? You know, right now I think we finished all the question online. And anyone in the meeting room have any question? Okay, if not, so I really like to thank Professor Guo for this excellent lecture. So so I would like to close this thinking lecture of from the ECTI, the lecture number 3. Okay, thank you very much.